They warp time. They swallow stars. They might even be hiding gateways to other universes. Black holes are some of the strangest objects in existence. But how do they actually work? Let's go beyond the void and find out. A black hole begins where a massive star ends. When a star about 20 times the mass of our Sun runs out of fuel, it can no longer resist the force of gravity pressing inward. With fusion shutting down, the core collapses under its own weight, forming a point of infinite density and zero volume, a singularity. Surrounding the singularity is the event horizon, the invisible boundary where gravity becomes so strong that not even light can escape. It's not a surface, but a one-way exit from our universe. Not all black holes are the same. Let's break them down. Stellar mass black holes are the most common. Formed from collapsing massive stars, they usually range from 5 to 100 times the mass of our Sun. One well-known example is Cygnus X1, about 6,000 light-years away, which is actively devouring its companion star and emitting powerful X-rays. Another, GX339-4, is among the smallest we've found, just a few solar masses, barely qualifying as a black hole. Supermassive black holes are the titans, anchoring entire galaxies. They can weigh millions or even billions of times more than the Sun. The Milky Way's core contains Sagittarius A, weighing around 4 million solar masses. But the largest ever discovered is TON 618. It's so massive, around 66 billion solar masses, that its accretion disk stretches across light-years and radiates more energy than 10,000 suns combined. Intermediate black holes are the elusive middle class, ranging from hundreds to thousands of solar masses. One candidate is HLX1, about 290 million light-years away, and estimated at 20,000 solar masses. They may form through the mergers of stellar black holes or within dense star clusters, but we've only found a handful of strong candidates so far. Then there are primordial black holes, still purely theoretical. Formed during the earliest moments after the Big Bang, these could be as small as atoms or as massive as mountains. If they exist, they might even help explain dark matter. So far, no direct detection, but scientists continue to search. As matter spirals into a black hole, it doesn't fall straight in. It forms an accretion disk, a glowing whirlpool of gas and dust spinning at near-light speeds. Friction in the disk generates extreme heat, sometimes over 10 million degrees Kelvin, making it brighter than entire galaxies. These violent regions are responsible for quasars, the brightest, most energetic objects in the universe, powered entirely by supermassive black holes consuming matter at staggering rates. So, what if you fell into one? That depends entirely on its size. A stellar mass black hole would kill you quickly. As you approach the event horizon, the gravitational gradient is so steep that your feet experience far more pull than your head. This effect, called spaghettification, would stretch and compress your body into a long, thin stream of particles, tearing you apart before you even cross the horizon. A supermassive black hole is a different story. The tidal forces near its event horizon are weak due to its enormous size. You could actually cross the horizon without feeling anything. But deeper in, near the singularity, the same fate awaits. Only now, you might have time to experience the fall. Seconds, minutes, maybe longer, depending on the mass of the black hole. Fall into an intermediate black hole, and the experience would be somewhere in between. You might have a few surreal seconds of awareness as your body stretches and burns from friction. Then, atomization. Primordial black holes, if real, could be microscopic. Falling into one might vaporize you in a flash. No stretching, just instant compression to the quantum scale. Some theories suggest that quantum gravity effects could emerge here, but we're deep into speculation. Do black holes last forever? Not quite. In 1974, Stephen Hawking proposed a revolutionary idea that black holes emit tiny amounts of energy over time, now called Hawking radiation. This means they lose mass very slowly. For a stellar mass black hole, this process would take trillions upon trillions of years. A supermassive one like TON 618 could take longer than the current age of the universe multiplied by a quadrillion. Black holes are not just massive, mysterious objects. They challenge the very nature of space, time, and reality. They are laboratories for the laws of physics, and possibly the keys to understanding the deeper structure of the cosmos. We still don't fully understand them, but we are getting closer with every question, observation, theory, and telescope. This is Beyond the Void. Subscribe to uncover more secrets of the cosmos, one singularity at a time.